Hello everyone, welcome back to my channel. Today we're going to work on another problem, finding the centroid by integration. So let's get started. You can see the problem here. Obviously this is more involved. It involves angles, etc. You can find more practice problems with centroids involving composite planes and finding centroids by integration at this link below. Unfortunately, it's not clickable, but I have attached it in the commentaries, and you can also just type it into your Google search bar if you need. So, this is the full problem statement. Determine by direct integration the centroid of the area shown. Problem. The solution, first, we will need to write the general equations. The sum of the moments about y is equal to the x centroid of the whole figure multiplied by the sum of the whole area of the shape, and that is in turn equal to the sum of the x centroid of every differential element in the shape times the very small area of each differential element in the shape. So over here, we will be dividing this shape into very, very small sectors, and then we'll be summing up those sectors. We'll be summing up the centroids of each individual sector and also the areas of each individual sector. So this is what this equation is talking about. Similarly, we can define the moment about x in a similar manner. The y corner of the centroid of the whole entire figure times the area of the whole figure, and that is equal to the y corner of the centroid of each piece that we choose to divide this shape into times the area of that small piece. So we can substitute from the diagram. As we saw before, this is what the x capital bar is referring to, the x corner of the centroid of the whole figure. And then the area of the whole figure, which is the integral of dA. And then we can divide this whole shape into many different sectors as such. And then the centroid of each will be lowercase x bar, basically. So lowercase x bar can be represented by 2/3 r cosine theta, and similarly lowercase y bar can be represented by 2/3 r sine theta. So what we have done here is we have noted the approximate locations of the centroid of each of these small sectors, and then we have drawn a triangle from each of the points where the sector intersects the curve. And then we can use right triangles to find the location of the centroid for each sector. Here is another clear picture, maybe. So we have first located the centroid of each individual small sector, and then lowercase x bar is the location of that centroid from the origin. And similarly, lowercase y bar is the location of the centroid in the y direction from the origin. Now we will want to substitute from the diagram. Let's zoom in a little bit with a magnifying glass. So zooming in like this, we can draw a triangle. Remember that the approximate location of the centroid is over here. On the top left-hand corner, I have given you the centroid of a right triangle. So we will be using that to help us out. Except over here, it's a little reversed, because keep in mind that the centroid is the centroid of the small sector over here. The small sector over here isn't exactly a right triangle. It's simply a sector we choose to divide it by. But below here, there are additional sectors. You can think about it like that. But the triangle is just to help us locate the location of the centroid in the center. So, keep in mind that the angle is varying. It's called theta. And we have the hypotenuse, which we call r. And then the adjacent, which we can find to be r cosine theta using the Pythagoras rule. And then the distance then will be r cosine theta times 2/3, which is equal to lowercase x bar. Similarly, lowercase y bar is equal to 2r sine theta over 3. Sine theta because now we are using the opposite side, which is this one over here. Okay, now let's write our equations. Lowercase x bar, as we said previously, is 2/3 r cosine theta. We have to substitute back in r from the problem statement, which is equal to ae to the power of theta. So 2/3 ae to the power of theta cosine theta. For y bar, which I've highlighted in green, we have 2/3 r sine theta, and that is equal to, substituting r again, 2/3 ae to the power of theta times sine theta. And then now this is our whole area. I've highlighted it in green. The area of a very small sector is called dA, a very small area. As you can see, this is an area of a small sector. Now let's think about how to express the area of a small sector or of any sector in terms of our given information. So if we start with a circle, a solid circle, a shaded circle, the area of the whole circle is pi r squared. Now, if we only take a small sector and we find the area of that sector, well, the angle of that sector is pi. The area of the whole circle, of course, is 2 pi. And then we can use kind of a proportion to find the area of the sector if we know that the area of a whole circle is pi r squared. So the area of this sector is going to be proportional to the ratio of theta to 2 pi. So we are going to have, for the area of a sector, pi over 2 pi times pi r squared. So pi over 2 pi is the proportion, and then we multiply that by the area of the whole circle to find the area of the sector. So simplifying, that is equal to theta times r squared over 2, where r is the radius. So this angle over here of this very small sector is called d theta. If that is so, the area of a small sector will be equal, dA will be equal to r squared over 2 times d theta. Going off of this equation over here, where we have substituted in d theta of a very small angle in place of theta. Now, the area of this whole shape over here highlighted in green will be equal to the integral of r squared over 2 d theta from 0 to pi. And I will show you how I got those bounds later. Okay, so dA, I have highlighted in orange. What is dA equal to? Well, dA is equal to r squared times d theta over 2. R squared times d theta over 2. So basically, we have taken simply this information from here, and this is equal to dA. Because the sum of this, remember, will give you the area of this whole thing. Now we can substitute in r again. R is equal to ae to the power of theta. So we have dA is equal to a squared times e to the power of 2 theta times d theta over 2. Okay, solution. Remember, this is all we have solved for now, up to this point. Now we will want to substitute in the given information. First, for the sum of the moments about the y. So that is equal to x bar times dA times, and that is equal to the sum of lowercase x bar times dA. Doing manipulation, we can simplify it into this equation. Now we will want to use the integration by parts. I have skipped that for now because it is very long, but you guys all know how to do this already. If you don't, I can create a new video showing you guys how to integrate by parts. After you integrate by parts, you will get this equation over here. Now we want to think about what bounds to use. Let's go back to our image over here. Well, theta is varying from 0 to pi. So we will simply use 0 to pi as our bounds. Now, further simplifying this equation, we have this equation over here. Dividing both and then simplifying further, we have this equation over here. Dividing both sides by a squared times e to the power of 2 pi minus 1 over 4. We will get that capital X bar is equal to negative 9.278. Now let's solve for the second equation by plugging in all our given information and everything we have solved for. We get first this equation, then this equation, then after integrating by parts, we get this equation over here. After plugging in the bounds, we get this equation over here. And then which simplifies to this equation, which simplifies to this equation, dividing both sides by a squared times e to the 2 pi minus 1 over 4, we will get that capital Y bar is equal to 3.09a. So that's all we needed to solve for. We needed to solve for the centroid, the x and y coordinates of the centroid of this planar shape. Thank you guys so much for watching this video, and I hope to see you next time.